Hello, in this lesson we are going to solve 3 problems related to the kinetic theory and discuss a little bit about it. Let's start with problem number 1. So it's known that the average atomic and molecular speeds are really large, and even at low temperatures. To show you that, let's calculate the average speed for helium atoms at 5 Kelvin. Okay, that's just 1 Kelvin above helium's liquefaction temperature. And also it's just 5 Kelvin above the absolute zero. Okay, I'm providing you the Boltzmann constant here that we're going to use in the kinetic theory relation. So we have that the kinetic energy can be related to the temperature. Alright? So before doing our calculations, we need to know the mass of the helium atom. And we know that it's 4 atomic molecular units. Alright? To transform it into kilograms, we just multiply it by 1.66 times 10 to the negative 27. And we have a mass of 6.44 times 10 to the negative 27 kilograms. Now we can just insert this value here in the formula and isolate the speed. Okay, so for helium at 5 Kelvin, it's always the absolute temperature here, we have an average speed of 179.3 meters per second. So even at very low speeds, we have very low temperatures, we have really high speeds. Alright, so for problem number 2, we also know that much of the gas near the sun is atomic hydrogen. Alright? And its temperature would have to be 1.5 times 10 to the 7 Kelvin for the average velocity to equal the escape velocity from the sun. So it's pretty high temperatures, right? So let's calculate this average velocity for this situation here. So this velocity equals the escape velocity from the sun. So here, the Boltzmann constant again, we can just use the same formula. It's the same problem basically, that's problem number 1. But here we are dealing with hydrogen. Okay, so we find the mass of the hydrogen, add the values in the formula, calculate the average velocity. And this is about 6.09 times 10 to the 5th meters per second. So it's really high if you think about it, right? If you think about Earth standards. But if you think about the speed of light in the universe, that's approximately 3000 times 10 to the 5th meters per second, is actually not that high, right? Okay, now for problem number 3, we know that the nuclear fusion, the energy source of the sun, hydrogen bombs and fusion reactors occurs much more readily when the average kinetic energy of the atoms is high. That is, at high temperatures, alright? So suppose you want the atoms in your fusion experiments to have average kinetic energies of 6.4 times 10 to the negative 14 joules. So what temperature is needed? Well, we always associate the kinetic energy with velocity, right, with speed. But we saw with the kinetic theory, we can associate it with the temperature. So what we can do, we can just use the temperature to calculate the kinetic energy, or the opposite. If you want a specific kinetic energy in your experiment, you can calculate what is the temperature that is needed for it. So it's pretty simple. You just add the values. We already have the kinetic energy, the Boltzmann constant, isolate calculate the temperature and find that we need a temperature of 3.09 times 10 to the 9 Kelvin. If you think about it again, it's very, very high, right? It's a very, very high temperature. But we actually achieved higher temperatures in the Large Hadron Collider. We could achieve colliding two particles a temperature of 4 times 10 to the 12 Kelvin. So if you think about it, it's pretty higher than this temperature here. So it's not impossible, okay? And also, if you think about the Planck temperature, it's much, much lower than the Planck temperature. That's 142 times 10 to the 32nd Kelvin. This Planck temperature is the temperature we believe that the universe was right after the Big Bang occurred.
Now that you watched this video, you're one step closer to achieving your academic goals. Well done! There's always more to learn, so check out our other videos and don't forget to subscribe.